Even though today this class is for physical chemistry 2, I would like to continue with the gaseous state. So I would like to make a presentation. So these are all the things what we have already seen. Um, the peculiar behavior of gases and the nature of the universal gas constant, and also what is normal pressure and normal temperature. And we have seen the characteristics of ideal gas by combining the three laws, namely the law of Robert Boyle and the law of Charles and the law of Gay-Lussac. And when we discussed these laws with their graphical representations and the mathematical equations, we could combine all these laws, and finally we could arrive at the ideal gas equation, which states that PV is equal to nRT. And we have also derived, we could calculate the value of universal gas constant with the help of ideal gas equation, and it came to 8.314 Pascal meter cube per Kelvin per mole, which is equal to 8.314 Joule per Kelvin per mole. So that is universal gas constant. Actually, we have seen the universal gas constant in a different view in thermodynamics, where we could say that it is the heat capacity of 1 mole of a gas, that is the quantity of the heat energy required to rise the temperature of 1 mole of a gas by 1 degree. So these are all the behavior of real gas. At low temperature and high pressure, real gases will undergo liquefaction, and after they become liquid, there is no further volume change. And in the case of isotherm, temperature is maintained constant and more pressure is applied. At high pressure, again liquefaction begins and no further volume change is observed in the case of real gases. So this liquefaction, the molecules coming closer and getting associated and becoming a liquid. You know that a liquid substance is containing molecules which are bound together by a bond, maybe a weak bond, but they are bound together. See why water is in liquid state? It is because of the hydrogen bond existing between the water molecules. So the gaseous molecules, when they are forced to be very close with each other, then the liquefaction begins. So at a low temperature, high pressure, liquefaction begins. In the case of isotherm, at a high pressure, when the temperature is maintained constant, the liquefaction begins. So as the usual property of liquid state, compressibility of a liquid is negligible. Therefore, the volume change after the gas becoming a liquid is not observed. Therefore, we could make the distinction between ideal gas and a real gas. Ideal gas is the one which does not have intermolecular interactions. And the real gases are those which have intermolecular forces or interaction. So this is what we have seen so far. And now, and also we have explained that the experimental pressure and the theoretical pressure for an ideal gas, they will be equal, but for a real gas, the theoretical pressure and the experimental pressure will be different, or the experimental pressure will get deviated from the theoretical pressure, and that is why the pressure of the real gas is called fugacity, that is called effective pressure. Actually, this effective pressure is by a pressure correction. The pressure correction is called internal pressure, which arises due to the intermolecular interactions. Therefore, the normal expected pressure plus or minus the internal pressure is equal to effective pressure. So that is what we have seen so far. Now look here, we are going to discuss the molecular motions in gaseous state. See, when a gas molecules are confined in a container, the gas molecules are in a state of a constant motion. They are all moving in all directions unceasingly. They do not stop. They are moving. But when you raise the temperature of the whole system, the molecules move with increased velocity. Why there is an increase in the velocity? The thermal energy supplied to the gas molecules confined in a container, it increases the kinetic energy of the gas molecules. So kinetic energy, you know, it is half mu square or v square. That half mu square increases. Therefore, the probability of molecules hitting with each other increases. And at the same time, number of collisions and also the colliding force, both are increasing. Therefore, the walls of the container are getting continuous hit with a high kinetic energy. Therefore, pressure also increases with the temperature. So this is the relation between temperature, kinetic energy, and the pressure. Therefore, when temperature increases, the thermal energy increases. The increase in the thermal energy increases the kinetic energy of the gas molecules. The increase in the kinetic energy increases the number of collisions, and the increase in the number of collisions again increase the force and also the number of hit on the walls of the container. Therefore, the pressure increases. The pressure is nothing but the total force acting per unit area on the walls of the container. This is how the pressure of the container, the pressure of the gas increasing with increase in temperature. Now, Maxwell's law. According to Maxwell's law, molecules have different velocities, which means that suppose in a container, thousands of gaseous molecules are present. All the molecules do not travel with the same velocity. Velocities of each molecule is different. So we cannot exactly say that these many number of molecules are traveling with this particular velocity. We can never define that. Therefore, we can only have a probability considerations. We can say that approximately this percentage of molecules are with this velocity, because the velocity of the molecules are different, and at the same time the velocities of the molecules will be continuously changing. A molecule which is moving with a high velocity now may move with a low velocity next moment. It may lose its kinetic energy. The molecule which is moving with a low velocity now may gain kinetic energy and may move with a faster rate. So the molecules are not having uniform one common velocity. They have different velocities. At the same time, we can never predict that one molecule will have a constant velocity. Its velocity is also changing. Therefore, we can simply have a probabilistic approach or probability considerations. and we can write an equation for this probability of velocity and the percentage of the molecules present. So look at this equation. This equation number 1. It is dnc by n is equal to 4 pi m by 2 pi rt whole power 3 by 2 and e power minus mc square divided by 2 rt c square dc. Look at here, look at this part of the equation. It is nothing but minus half mv square. Actually, it is E, the kinetic energy. So instead of writing it is half mc square, it is just written as mc square by 2 rt c square dc. What is this dnc? dnc is n by total number. That is, it is the fraction of the number of molecules with velocity between c and c plus dc. See, if you do not understand this, you just have an idea like this. Suppose c is a 10 kilometer per second. I want to have a small deviation, and the next velocity, let me say it is 15 kilometer per second, means what is the fraction of the gas molecules having the velocity between 10 and 15? That is the thing. So dnc is the fraction of the gaseous molecules having the velocity between 10 and 15. So this dc is supposed to be a very small quantity for a small deviation, So that is the dnc, where m is the molecular weight and t is the temperature in absolute scale. In order to make you remember that we derived an absolute scale of temperature, that which is also called the gas scale of temperature. I have put the word gas. Otherwise, you need not have the word gas here. It is the temperature in absolute scale. Therefore, m is the molecular weight and T is the temperature in absolute scale. Now look here, the equation number 1 divided by dc, you will be getting 1 by n can be taken out because this is 1 by n dnc, no? So 1 by n dnc by dc is equal to 4 pi, it is m 2 pi rt whole power 3 by 2 and e power minus mc square divided by 2 rtc square. Actually, this c square is there, that dc has vanished because that dc, we have divided the whole equation by dc. Therefore, the one dc is introduced here and that dc which was on the right hand side has vanished. This equation 2 is called Maxwell's law of distribution of velocities. This is called Maxwell's law of distribution of velocities. So once again, I would like to explain this. dnc is the fraction of the gas molecules with velocity between two limits. That these two limits should be very close to each other. You should not say it is 10 meter per second to 100 or 1000 meter per second. No, such a long gap you should not consider. Because if you take the long gap, this is something like asking in the class, how many students have got mark between 70 and 80? You should not ask how many students have got mark from 0 to 100. Everybody will be there. All the students would have got some mark between 0 and 100. There is no meaning in finding out the percentage of students got marks between 0 and 100. You have to find out the number of students got the mark between 90 and 100. This is a meaningful approach. Or 90 and 95. What the gap, when you narrow down the gap, the meaning is more. If you broaden the gap, the meaning is less. So this is how the Maxwell's law of a distribution of gaseous velocities has been derived. Now look here, that left-hand side part of the Maxwell's law of a distribution of velocities is 1 by n into dnc by dc. This is called the probability of finding the molecules having the velocity c. What is the probability of finding the molecule having the velocity c? You should understand first of all what is a probability. Probability means what is the desired result among a desired result with divided by the total number of results possible. So probability of finding the molecules having velocity c means, suppose if I have 100 gaseous molecules, what is the probability or what would be the approximate number of molecules having the velocity c? I am defining a velocity c. I can have any velocity, say 10 meter per second. What is the probability of finding the molecules with velocity 10 meter per second? If the probability comes to be 20, which means that among the 100 molecules of gases, approximately 20 molecules we can find with velocity 10 meter per second. So this is the approach. I suppose all of you understand what I have told you. So it is the probability of finding molecules having the velocity c. I can decide any velocity. Say for example, from 0 to, let me say the maximum velocity is some 100 meter per second. Now I calculate what is the probability of finding molecules moving with velocity 10 meter per second. What is the probability for 20 meter per second? What is the probability for 30, 40, 50, 60, 70, 80, 90 and 100? So I can plot the probability of finding the molecule having the velocity, a particular velocity along the y-axis and the velocity along the x-axis. Or I can tell you in a different fashion. Suppose in the y-axis, I am taking the number of students got the mark. In the x-axis, I am plotting the mark 0 to 100. Then what will happen? The graph will be like this. Look at the graph. On the y-axis, I have taken percentage of molecules. On the x-axis, I have taken the velocity. You need not get confused by looking at all the graphs. You look at only one graph. That graph corresponding to the temperature T1, which is the least one. See the least temperature, the graph So look at the graph. So this is the velocity from 0 to some maximum value. This is percentage of molecules. So 10% to 20%, 30%, 40%, like something like this. So the percentage goes on increasing at a particular temperature. So the percentage of molecules with 0 is very little. The percentage of molecules with 10 meter per second, 20 meter per second, 30 meter per second, and it attains a peak, which means that more number of molecules are moving with velocity this. And again, it decreases. And it decreases. Decreases means the number of molecules having the velocity decreases, velocity increases. Highest velocity also, less number of molecules. So highest velocity also, less number of molecules. The least velocity also, less number of molecules. This is something like this. The number of students getting 0 mark in the class will be very less. Number of students getting 100 mark in the class will also be very less. Number of students getting marks from 40 to 60 will be the more. So something like this. So this is the least velocity and this is the highest velocity. So the velocity increases means the number of molecules also increasing, and then it attains a peak, and then it comes back, and finally it goes to zero here. So when you raise the temperature, now I increase the temperature. When I increase the temperature, the number of molecules with a particular velocity increases, but the peak velocity is shifted towards right. So this is the highest velocity. Velocity is higher at a higher temperature, but the number of molecules having that particular velocity comes down. Similarly, when you raise the temperature further, the velocity increases, kinetic energy increases, but the number of molecules with that particular velocity decreases, because in the first case, the graph is little bit sharpened, but in the second case, it is a little bit broader. That means more number of gas molecules move. Among them, a little with the highest velocity. So again, for next higher temperature, it gets broadened like this. So this is how with the temperature, the molecular velocity increases. Actually, the peak where the more percentage of molecules having that velocity is called the most probable velocity. The most probable velocity. And slightly less than that is called mean velocity. And slightly less than that is called root mean square velocity. Later on, we are going to discuss what are they. So from the curve, so this is the graph we have drawn by taking the Maxwell's distribution law into consideration. This is actually the graphical representation of the Maxwell's distribution law. Now, from the graph, from the curves we have drawn so far, what are the important features of the motion of the gas molecules we are going to find out from the graphs? Number one, the fraction of the molecules with too high velocity and too low velocity are very small. And there are certain velocity for which the fraction of molecules is maximum. So these are the two important features of the graph. So number one, the molecules with high velocity is also less. Number of molecules with low velocity is also less. And number two, there is a particular velocity in which more number of molecules are moving. So these are the two important features of the curve. Now, what is the most probable velocity? The most probable velocity of a gas is the velocity possessed by maximum number of molecules of the gas at a given temperature, which means that also changes with the temperature. See, if for the temperature T1, this is the most probable velocity. For the temperature T2, this is the most probable velocity. For the temperature T3, this is the most probable velocity. For a particular temperature, the most probable velocity is the velocity possessed by maximum number of molecules of the gas. Therefore, the most probable velocity changes with the temperature. But what is most probable velocity at a given temperature? What is the velocity possessed by maximum number of molecules? So this is what corresponds to the peak of the curve. The most probable velocity is at the peak of the curve. And also, when temperature is maintained constant, it depends upon the volume of the gas. If you increase the volume of the gas, then the percentage of the molecule will also increase, because more number of gas molecules will move with the most probable velocity. Say if you do not understand, let me explain like this. Suppose you have a balloon filled with 100 molecules of gas, in which say some 60% or 60 molecules are moving with the most probable velocity. Now I am increasing the volume, and now I store 200 molecules of gas. Now what will happen? Nearly 120 molecules will be moving with the velocity. the most probable velocity. Therefore, when temperature is a constant, the most probable velocity depends upon the volume of the gas. So if a volume is more, if a volume is less, then that will affect the most probable velocity, provided temperature should be constant. If you are changing the temperature and also the volume means, that will be totally confusing. You cannot arrive at a conclusion. Either you have to maintain the volume constant and change the temperature and note down the most probable velocity, or you have to maintain the temperature constant and then the relation with volume has to be found out. You need not, you cannot change both the variables. So at a constant temperature, the most probable velocity depends upon the volume of the gas. So that is very important. So I have told you the definition for the most probable velocity, which is the velocity possessed by maximum number of molecules of the gas at a given temperature. So it corresponds to the peak of the curve, and also when temperature is constant, it depends upon the volume of the gas. So this is these are the significant features we are getting from the curve. Now the next one, look at this. The effect of temperature on the distribution of molecular velocities. So you have to concentrate a little more to understand this particular concept. It is the effect of temperature on distribution of molecular velocities. So I have already told you the most probable velocity increases with increase in temperature. Why? How can you account for this? Look at the equation. Which equation? That Maxwell distribution equation, or Maxwell's law, or Maxwell law of distribution of velocities. Look at this equation. In this equation, there is a term like this: e power minus mc square divided by 2rt. An exponential part is found over here. You have to carefully look at the exponential part of this equation. And this equation, this part, look, a minus sign is there, and also the temperature is found in the denominator. So the minus sign and the temperature found in the denominator, see, if the minus sign alone there, what will happen? If anything in the numerator increases, the value decreases. If minus sign is not there, anything in the denominator increases, the value increases. Now the minus sign is there, at the same time the temperature is found in the denominator. So these two things indicate that the temperature and the entire exponential value are directly related. So the most probable velocity increases when the temperature increases. So this particular part, e power minus mc square divided by 2rt, is called Boltzmann factor. This is called Boltzmann factor. So from this, minus 1 by 2 mc square is called kinetic energy E. So this minus sign is put over here also. So the kinetic energy is increasing when the temperature is increased. So this understanding finds its place in the reaction rate studies also. Later on, you are going to study the kinetics of chemical reactions. Why chemical reaction kinetics, or why the rate of the reaction increases with the temperature? Because the molecular kinetic energy is also increasing. So this increase in the kinetic energy with the increase in the temperature, it shows that it has its role in the reaction rates also. So we will be very soon discussing the Arrhenius equation in the chemical kinetics, where the rate constant and the temperature are related. There you will understand why it happens like this. Now I can say this is called the Maxwell-Boltzmann's law of distribution of velocities, that is N2 by N1 is equal to e power minus E by RT. Look at this equation. Now you can have a doubt, sir, a molecule is with a particular kinetic energy. Whether N1 number of molecules are with the kinetic energy E or N2 number of molecules are with the kinetic energy E, actually this E is the difference between the energy of N1 number of molecules and N2 number of molecules at a temperature T. N1, the number of molecules in a particular energy level. N2 is the number of molecules in a different energy level, whereas the difference is E. So this ratio, that is N2 by N1 ratio, can be found out by using this equation E power minus E by RT at a temperature T. So that is what you should understand from this equation.